Now recall our original goal was to find the projection of a vector B orthogonal to a vector space big V spanned by some arbitrary vectors. And all we've been able to do so far using project orthogonal is find the projection of B orthogonal to the space spanned by mutually orthogonal vectors. So how are we going to go about solving this original problem? Well, the procedure we have would suffice if only we had a way of going from arbitrary vectors v1 through vn to mutually orthogonal vectors v1 star through vn star that happen to span the same space as v1 through vn. This is called orthogonalization. We're given vectors v1 through vn, and we want to produce a list of mutually orthogonal vectors v1 star through vn star such that the span of those vectors equals the span of the original vectors. How can we solve this problem? Here's the key idea. We're going to use project orthogonal in an iterative fashion to make a longer and longer list of mutually orthogonal vectors. So let's start with v1. We define v1 star to be just v1, since the set consisting just of v1 star is trivially mutually orthogonal. Next, we define v2 star. Well, what's v2 star? v2 star is the projection of v2 orthogonal to the vector that's already in our list, v1 star. Now, since v2 star is orthogonal to v1 star, our set is a set of mutually orthogonal vectors. Now let's move on to v3. We define v3 star to be the projection of v3 orthogonal to both v1 star and v2 star. So the set v1 star, v2 star, v3 star is a set of mutually orthogonal vectors. In each iteration, all we have to do is project a vector orthogonal to a collection of mutually orthogonal vectors. And we can use project orthogonal for that. So in the ith iteration, we project the ith vector in v-list, vi, orthogonal to the i-1 vectors that are already in our mutually orthogonal list, v1 star through vi-1 star. And that's how we find vi star. We just add that to the list. So here's the procedure. It's given a list of vectors, v-list. Initially, the list of mutually orthogonal vectors is empty. The procedure iterates through the vectors in v-list, and for each one, projects that vector orthogonal to the vectors already in the list of mutually orthogonal vectors, v star list, takes the result and appends it to v star list, preserving this property that all the vectors in v star list are mutually orthogonal. At the end, the procedure returns the value of v star list. So it's pretty easy to see that at each stage in the algorithm, the value of v star list is a list of mutually orthogonal vectors. In particular, at the end, the value returned consists of mutually orthogonal vectors. So here's an example. Let's say we run orthogonalize on the list consisting of these three vectors. We'll show that it returns the list consisting of these three vectors, v1 star, v2 star, and v3 star. In the first iteration, the vector v is v1. The v star list is empty, so the first vector added to v star list is just v1. The next iteration, we're working on v2. V star list consists only of v1 star. So the procedure projects v2 orthogonal to the list consisting only of v1 star. And this is the vector it comes up with. So this is the vector that's added to v star list in the second iteration. In the third iteration, when we're working on v3, v star list consists of v1 star and v2 star. So we take v3, project it orthogonal to v1 star, getting 0, 0, 2, and then take that vector and project it orthogonal to v2 star, getting 0, -1, 1. So this is the vector that's added to v star list. This is v3 star. As we mentioned before, at any point in the algorithm, the vectors in V star list are all mutually orthogonal. But what we need to show that after I iterations of the algorithm, the span of the vectors in V star list at that point equals the span of the first I vectors in V list. And we use induction. The case I equals 0 is trivial. So we do the induction step. After I minus 1 iterations, V star list consists of the vectors V1 star through Vi minus 1 star. Now, assume the lemma holds at this point. That means that the span of these vectors, V1 star through Vi minus 1 star, equals the span of the first I minus 1 vectors in V list, V1 through Vi minus 1. Now we take the vector Vi, we insert it into both of these sets. Well, the span of this set is still equal to the span of this set. So what we need to show is that the span of V1 star through Vi minus 1 star together with Vi equals the span of V1 star through Vi star. The ith iteration computes Vi star by projecting Vi orthogonal to V1 star through Vi minus 1 star. Therefore, there are coefficients such that this equation holds. Vi is the linear combination of V1 star through Vi star. Well, this equation shows that any linear combination of V1 star through Vi minus 1 star together with Vi can be rewritten as a linear combination of V1 star through Vi star, because Vi can be written in that way, and vice versa. So this shows the induction step and completes the proof. Now notice that the order of the vectors in V list does matter. If you ran the procedure orthogonalize with different orders on V list, you'd get different answers. This is different from project orthogonal because the projection of a vector orthogonal to a vector space is unique. There's only one such projection. So at least in principle, the order of the vectors in V list shouldn't matter. Now, for project orthogonal, we were able to express the result using this matrix equation. The vector B is the product of this matrix, columns V0 through Vn and B perpendicular, times this column vector. For orthogonalized, we have the following equations. V0 is just V0 star times 1. V1 is the matrix with V0 star and V1 star as its columns, times this column vector, V2, V3, and so on. We can combine all these equations in a single matrix-matrix equation. The matrix whose columns are V0, V1, V2, and V3 is the product of the matrix whose columns are V0 star, V1 star, V2 star, V3 star, times this matrix. In general, the solution looks like this. Now notice that these two matrices have a special form. The columns of this matrix are all mutually orthogonal. And this is an upper triangular matrix. So we'll use those properties later on in algorithms. Here's an example. If V list consists of V0, V1, and V2, the output V star list consists of V0 star, V1 star, and V2 star. We'd write the matrix equation in this way. These are the input vectors. These are the output vectors. These columns are mutually orthogonal, and this is an upper triangular matrix. Now let's get back to the original problem. We're given a vector space, big V, which is expressed as the span of input vectors V0 through Vn. The vector in big V that's closest to B is B parallel, which is B minus B perpendicular. So how can we find B perpendicular? There are two equivalent ways. Here's one method. We first apply orthogonalize to V0 through Vn. So we get V0 star through Vn star. These are mutually orthogonal, and they span the same vector space as V0 Vn, namely big V. Now we can call project orthogonal with B as the first argument, and the list consisting of v0 star through vn star is the second argument. This satisfies the spec of projector orthogonal because v0 star through vn star are mutually orthogonal. So we get the correct result. So here's another method. We just call orthogonalize with an input list consisting of v0 through vn together with b. And exactly the same computations take place. We get as an output the list consisting of v0 star through vn star and a final vector I'll call b star. Well, in the last iteration of orthogonalize, the vector b star is obtained by projecting the input vector b orthogonal to the previous starred vectors v0 star through vn star. So that also gives you b perpendicular. We've shown how orthogonalize can find the vector in span of v0 through vn closest to b, namely b parallel. And later we'll find out how to give the coordinate representation of b parallel in terms of these vectors. For now, we're going to look at how we can use orthogonalize to give algorithms for other problems. So let's start with a mathematical result about mutually orthogonal vectors. We'll show that mutually orthogonal non-zero vectors are linearly independent. So let v0 star through vn star be mutually orthogonal non-zero vectors. We'll show that these vectors are linearly independent by showing that if you can write the zero vector as a linear combination of those vectors, then the coefficients, alpha 0 through alpha n, must be 0. So here we'll show that alpha 0 is 0. We do that by taking the inner product with v0 star on both sides of the equation. On the left side, we take the inner product of v0 star with the 0 vector. And on the right side, we take the inner product of v0 star with this whole expression, which, using algebraic properties of inner product, we can replace with this expression. So now let's look at each of these inner products. The inner product of v0 star with v0 star is the norm squared of v0 star. These other inner products are all 0 because the vectors are mutually orthogonal. So we end up with alpha 0 times the norm squared of v0 star. Now, this inner product, v0 star with the 0 vector, is 0. So we've shown that alpha 0 times the norm squared of v0 star is 0. Well, since v0 star is a non-zero vector, its norm is non-zero. So the only solution to this equation is alpha 0 equals 0. So we've shown that alpha 0 must be equal to 0. The same argument can be used to show that all the other coefficients also have to be 0. And that completes the proof.